Before I start, I would like to thank the organizers, Roland and Pavlo, for inviting me to this beautiful symposium. And here are my slides. And the topic of my talk is the recent progress that we have done on a family of methods that loosely we call them data-driven quantum chemical methods, where we combine quantum chemistry together with machine learning. And I'm saying loosely called data-driven because in reality, these are data-driven methods, but physics-inspired methods. And I hope I will convince you that indeed we encode the proper physics of the problems that we are trying to tackle. Before I start with my talk, I would like to introduce some current challenges that we face as a community, and most of the speakers in this symposium have already addressed these issues during their talks. For example, one of the main challenges that we have is the lack of large, homogeneous, and reliable data sets. And I think that Rocio earlier framed that problem very nicely. And usually our approach is to generate data sets by using computational methods. And based on this data, we can develop high-throughput workflows. Another important problem that we have as a community is the effective application of AI. And in order to, we're not yet ready to just ask a question to a computer and just get an answer from that. So still we need to introduce also domain and application expertise. And I think that it was Ignacio that in your talk you have a statement at the conclusions where you highlighted how important it is to introduce this kind of domain expertise when we develop new models. And the third problem that we face, mainly not for experts like we are, or most of us we are, but when we are introducing these kind of methods to the next generation of chemists, how we actually teach these methods to them. Because right now, machine learning is not part of the traditional chemistry curriculum. So for that reason, we have contributed with new courses, with new teaching material, and with many textbooks and hands-on examples. For example, the US NSF-funded MOLSI Center has done a lot of effort on this direction. They have developed beautiful online courses and material for teaching programming, computational chemistry, and machine learning to non-experts. We have contributed in this effort by writing and publishing recently an e-book on molecular representations. So in other words, how we encode chemical information in such a format that the computer can understand it and use it successfully for machine learning. In our book, we have organized these methods into 3 different categories: the graph-based representations, topology-based representations, and physics-based representations. This e-book is mainly for undergrads or first-year graduate students, PhD students, and that's why we have hands-on examples, and we describe established and popular representations, emerging methodologies, and we have also code examples that can be used directly from non-experts. The first part is about graph-based representations, which is mainly inspired by recent progress in chemoinformatics, and we have already discussed some of these topics in this meeting as well, especially SMILES and other similar representations. The second part is about topology-based representations, and in particular representations that they are based on persistence homology. If you want to learn more about this kind of representations, we can discuss after the end of my talk. We have done some work on this direction where we can actually encode topological information of molecular structures in our input vectors for machine learning. And finally, and this is more at the core of this symposium, physics-based representations, which cover from Coulomb matrices and their derivatives, atom-centered symmetry functions that we extensively discussed the first 2 days of this meeting, and of course, representations which are based directly on the information that we get from ab initio methods. And this is more or less the topic of my talk. So in our work, our inspiration was to, and still is, to recycle wave functions, to recycle information that we generate when we run quantum chemical calculations. And our aim is to start with calculations from small systems like those, generate data, and introduce this data into machine learning models in order to be able to run calculations on larger and more challenging systems. Our initial starting point for this family of methods is coupled cluster, in particular coupled cluster singles and doubles. In CCSD, we have an exponential coupled cluster ansatz, where we have the exponential operator, the exponential cluster operator that includes excitations or promotions of electrons from the occupied orbitals to the unoccupied orbitals in order to capture the correlation energy of a molecule. In CCSD, singles and doubles, we try and get this expansion after the first and the second electron excitations. The T1 operator promotes these electrons from the I occupied spin orbital to an unoccupied A spin orbital, and this comes together with an amplitude, a T1 amplitude, which is nothing else but the weight or the importance of this particular electron promotion. And the doubles excitations include, again, excitations of two electrons from the occupied IJ to the unoccupied AB spin orbitals. We don't solve this method in a variational manner, but on the contrary, what we do, we are solving a set of project equations in an iterative fashion. This is the standard methodology that we are following for solving the coupled cluster problem. In particular, we project our coupled cluster equation with respect to the zeroth order wave function, which is typically a Hartree-Fock wave function. And from there, we can compute the energy, which is now parameterized with respect to the T1, one electron promotions, and T2, two electron promotions amplitudes. We also have another set of equations with respect to the singly excited determinants and the doubly excited determinants. So we have enough equations in order to solve it exactly, in order to generate and to compute accurately the T1 and the T2 amplitudes. So once we solve this problem iteratively, we have now all our parameters for the coupled cluster energy function, and from there we can calculate the coupled cluster energy at the singles and doubles level of the theory. In conventional implementations, the T1 amplitudes are initialized by setting them equals to 0. And the reason is simple because their number is small, we can convert them this fast. On the contrary, the T2 amplitudes, which is the actual bottleneck of the method, they are significantly more than the T1 amplitudes. And as an initial guess in conventional implementations, we start with the MP2 amplitudes. So we start by using a cheaper level of theory as our initial guess for solving these projected equations. The T2 amplitudes are given here, and this is nothing else but the two-electron integral over the energy difference between the orbitals, the occupied orbitals, and the unoccupied orbitals. So a few years ago, we make a hypothesis together with my student Jacob, and in our hypothesis, we ask ourselves, can we get information from the cheaper level of theory, the MP2 level of theory, in order to construct a model, a machine learning model that can predict or learn, if you prefer, the higher level amplitudes at the coupled cluster level? So in order to do that, we decompose each two-electron excitation between IJ and AB spin orbitals into individual terms with respect to the orbital energies, but also the 1 and 2 electron Hamiltonian terms. We use this information as an input vector. In total, we have 30 different features. That was our initial input vector. And we introduce this as input for machine learning models. And from there, we are able to predict these T2 amplitudes. So in other words, in our scheme, our aim is to encode information from wave functions in order to predict parameters of higher level wave functions. And the workflow is the following. We start by doing a Hartree-Fock and an MP2 calculation. We extract the features that we need. We train our model. And from that model, we have predicted amplitudes. From that point, we have two different paths. The first is to plug these amplitudes directly to the energy expression of the coupled cluster and obtain an, we call it alchemical coupled cluster energy, which is very close to the exact, but it's not the exact. Or we can use these predicted amplitudes as initial guess to our projected equations that I showed you earlier, and from there recover the exact coupled cluster energy. So in principle, our scheme is an exact scheme, but we accelerate its convergence by using machine learning. And currently, we are exploring now molecular gradients by using a similar protocol. We also found a few years after we published our initial paper that we were not the first who were thinking along this direction. So actually, 15 years before us, there was another paper from our next speaker, Professor David Yaron, who thought about the same direction in order to develop same empirical methods. I wish we had found that paper earlier to give you actual credit, but I believe it's never too late. All right, so just as an example how the method is working, we have here data from 4 different molecular conformations of water, and we are using test conformations for testing the method. The conventional coupled cluster method has a difference between the 0th iteration of the projected, of the solvation, of the iterative solver of coupled cluster, and the final converged energy of 6.5 millihardt for these 10 water molecules. So in other words, 6.5 millihardt is the distance that I need to cover when I solve iteratively the set of projected equations. On the contrary, when I plug my predicted amplitudes, this difference drops to about 0.04 millihardt. So in other words, we are very close to the exact energy of coupled cluster. So I can either stop here and take this energy and continue with what I need to do, or I can use this as initial guess for solving further the projected equations, and in that case, we have a speed up of about 50% in terms of number of iterations. So one of the highlights of our first work was the demonstration of transferability between clusters of waters. So we consider 4 different water hexamers. In this case, the correlation energy between MP2, 0th iteration, and converged coupled cluster energy is about 0.09 Hartree. Now here, notice that we have more correlation energy because we have electron promotions also between water molecules, one water molecule to another water molecule. So in other words, here we consider also the correlation energy of the hydrogen bond network. We started by training models with water monomers, and in that case, the error jumped to almost 0.15 Hartree. So this model was even worse than the original conventional MP2. The reason is simple. Our model has no information about electron promotions between neighboring water molecules. So when we start now training models with water dimers, this error dropped to almost 0.01 Hartree, and together with trimers, the error is almost at 0. So in other words, the model can actually learn the physics, or the chemistry if you prefer, of these water clusters. In a separate study, which was more like an exercise for us, so in this case, we don't use the amplitudes, but we train on the pair energies, we explore the effect of locality on similar machine learning models. And we found that if we train with this kind of models, where we have the same input vector, but our aim now is pair energies, we can now accelerate the convergence and the accuracy of these models. And as an example here, I'm showing a model that was trained on propane through heptane, linear alkanes, and it was able to predict the coupled cluster singles and doubles energies for lengthier alkenes, can also go up to 18. So now we are taking this information or the knowledge that we acquired from this study, and we are trying to build it to put it back on our initial DDCC scheme. For this application, we use a peculiar set of molecules, or targeting molecules. So we constructed potentials by rotating this carbon-oxygen bond. Okay? So this is the potential of the rotational of these CO bonds. And I'm saying it's peculiar because even if this looks as a naive and straightforward study, the potentials actually have completely different barriers. This one is almost a flat potential, but on the contrary, the other, the more bulkier molecules have significant larger barriers, rotational barriers. So we tested 2 different learning, machine learning models, k-nearest neighbors and XGBoost. And what we found is that with canonical orbitals, we have more or less 5 millihartree error for the KNN model. But when we introduce locality, the error drops to almost an order of magnitude for both models. Of course, KNN is not portable model, especially now that we are trying to go to larger and larger molecular systems. So now we have switched to XGBoost. And actually, we are fine if we sacrifice a little bit of the accuracy. The new bottleneck now that we are facing is actually the amplitude space that we are screening through this model. So in other words, what kind of data we introduce to our machine learning models. Unfortunately, when we plotted all our data from this data set, we found this peculiar distribution of data. The majority of our data are around 0. And the reason is simple, that the majority of these 2 electron promotions provide close to 0 correlation energy, with some exceptions which are outside of this range. So this is the same data, but shown in the logarithmic scale. And in this case, you can see again that we have, when we train a model with this data, we're overpopulating this region, and we have underpopulated the most interesting side of our amplitude space. So in order to solve this issue, we have developed now 5 different selection schemes. I will not go into all the details of these models. I just want to highlight what is the outcome of these models. The first 2 are models where we are giving a score to every amplitude based on this function, for example, or based on k-means clustering. And based on these scores, we are organizing them in different bins, and we select specific number of amplitudes per bin. So now we can sample better our full amplitude space. The other two models are more chemistry-oriented models. In this case, we set a threshold, and based on that threshold value, we will accept or we will reject a specific amplitude. In the large amplitudes model, every MP2 amplitude that's below that value will be excluded for training, and every MP2 amplitude above our threshold will be included in our training. And this is usually similar to what people are doing with the PNOs in coupled cluster. The second scheme considers the electron correlation from the MP2 level. Again, if this value is above a specific threshold, it will be included on our training set. If it's below that threshold, we will exclude it. And finally, we have also probabilistic expression that again can allow us to select which data will be included or excluded. So to summarize, in this plot, we see what is the effect of all these models. So the black regions that you see here are the regions of the amplitudes which are excluded from our training sets by using the different models. And as you can see, all of them exclude the majority around 0, but some of them actually exclude some of the data that initially we would like to keep them in our sets. So what's the outcome now here? In this plot, I'm showing you the error that we introduce by training different models with different percentages of the total amplitudes. This dashed line is the error from the full model, where we consider all amplitudes. And as you can see, all our models actually converge asymptotically towards the full model. Some of them converge slower. For example, the score to bins that I showed you earlier has a slow convergence. If we select randomly amplitudes, we have this slow and oscillatory convergence. Some other schemes, like the k-means clustering, has faster convergence. Our probabilistic selection seems to be the best, based on this data. But we also found some interesting behavior from the chemically driven amplitude selection schemes, where about 15 or 20% of our total amplitudes, we can reduce the error of the full model. So we believe actually that these models can actually exclude some data, and we can avoid overfitting of the model. So in other words, now we are able to get similar accuracy when we're using a smaller fraction of the total amplitude space. And the same holds also when we move to larger basis sets. Again, the chemically driven approaches and the probabilistic approaches have accuracy significantly lower than the other two. If I introduce the same behavior in order to converge the actual coupled cluster equations, we saw these interesting behaviors. Here we have the correlation energy difference from the different models with respect to the number of iterations. And this is the conventional coupled cluster, which again has a slow convergence to the exact energy. With localized orbitals, we have even slower convergence. But on the contrary, our data-driven coupled cluster schemes start at 0 iteration close to 0. There's better behavior when we use localized orbitals than the canonical orbitals. And the same holds also for both full model or the model that uses, I think in this case, about 20% of our initial data. You cannot see the two plots because they are superimposed for the localized and the canonical orbitals. However, in all these cases, we're already very close to 0. We see this peculiar kink here. I'm pretty confident that once we solve this issue, because instead of going asymptotically directly to 0, we have this peculiar kink. Once we solve this issue, we can have an even faster convergence, and we can get the exact coupled cluster energy in less computational effort. We also found something very exciting, that if we plug the predicted amplitudes into the parenthesis T equations, we can recover also the parenthesis T energy. In this case, we have water molecules, and we dissociate the OH bond symmetrically for the both OH bonds. And you can see that both curves, the coupled cluster singles doubles and the CCSD parenthesis T, are superimposed with the data-driven scheme. And the parenthesis T actually term, even if it has different magnitude as we move away from the equilibrium of these bonds, the parenthesis T correction, the DT parenthesis T that I call here, is always flat, close to 0, as I move away from the equilibrium. So this correction doesn't introduce additional error to our initial DDCC scheme. So for the remaining 5 minutes, I would like also to introduce another scheme that we recently developed, where we target also the strong correlation of molecules. And in particular, we were interested in a method that is called two RDM or two reduced density matrix methods. In these methods, the idea is that we don't use many electron wave functions in order to predict the energy or to compute the energy, but we're using reduced density matrices. So in particular, we can express our energy with respect to 1 and 2 RDMs, and these 1 and 2 RDMs should include also information about the full N electron problem. So, so practitioners of the 2 RDM methods, what they are doing, they are applying specific conditions or constraints, if you prefer, on the development of the 1 and 2 reduced density matrices. They call this as N representability conditions. And from them, they are recovering the full correlation energy of these molecular systems. Recently, or not so recently, back in 2016, our friend and colleague from Florida State University, Eugene DePrince, came up with a scheme that combines V2RDM together with CASCI. And with this scheme, he is able to capture the strong correlation of ascenes, that are shown here. In particular, he was calculating the singlet and triplet gap with his method. And as you can see, he can go accurately and calculate at very large ascene molecules this singlet triplet gap, far beyond the limit of traditional CCSD 18,18. Of course, Eugene was not aware that at the same time we were working on high-performance computing for CCSD. So with our implementation of CCSD with parallel computing, we were able to do even larger active spaces. This is a different story. So V2RDM CASCI seems to work fine for larger systems. However, if we look more carefully, there are still deviations from the full CI problem. So in this curve, I'm showing to you the dissociation of N2 for the singlet state. And as you see, yes, the V2RDM is almost close, very close to the full CI. However, if you look more carefully, there is a big error as we move far away from the equilibrium and before we reach the dissociation limit. This error can reach close to 21 millihartry. So we came up together with an idea to use a similar data-driven approach, or if you prefer in this case, it's more like a delta ML approach, where we are targeting to estimate through machine learning the error of V2RDM with respect to the full CI problem. We use the domain expertise from the V2RDM practitioners, so we use features. We use a physics-based representation that utilizes features from the end representability conditions, but also partial three-particle conditions. This is what they call as T1 and T2. These are information for three-body terms that they do not explicitly depend on the three-body terms, so they can actually obtain this information from two-body or two RDMs. So our actual input includes entropy of the RDMs, traces and norms of the cumulants, shown here, and also the violation of these T1 and T2 conditions. So in this case, we use also kernel-less regression for training these kind of models. So what we found is that, we also did that by using an extensive data set. We have 36 different diatomic molecules. We consider the singlet and the triplet states for molecules that have an even number of electrons, or doublet and quartet spin states for systems with an odd number of electrons. We also consider different basis sets, and as you can see again, we have a wide variety of errors or deviations between CI and V2RDM, which maxes out at the distance between the equilibrium and the dissociation for both ground spin states and excited spin states. So with this model, we're able now to reduce the error from these molecules. For example, for N2, this error that maxed out before at 21 millihartry, now it has a mean absolute error of about 0.5 millihartry for both singlet and triplet state. So when we did the same analysis for all these species, we found that we can reduce the error between the ground spin state of these diatomics of about 1.78 millihartry. And it's more or less the same for the excited spin states, which are again 1.75 millihartry. We also applied a technique that is called Shapley additive explanation analysis, or SAP analysis, in order to extract additional information about the input that we introduce in these models. This is a tool that comes from cooperative game theory. So the idea here is that I'm playing cards, and every time I'm running this game, I'm excluding a feature, I'm excluding a card, and I can estimate in this fashion what is the outcome from on the accuracy of the model. So at the end, the model comes here with some scores or sub-values, and based on these values, we can estimate how important specific features are with respect to other features. So we got two different take-home messages from this particular study. The first one is that, yes, some features are more important than others. We knew that. In particular, we found that the average violation of the T2 conditions is more important than other features. Also, entropies of the alpha and beta blocks of the one-hole RDMs are important. However, what is more important for us is that all these features, they're within a very narrow, the top features differ by one order of magnitude from the rest, which tell us that in principle, this input vector is actually a good vector. It has been properly selected for this particular application. From our experience with sub-theory, with sub-analysis, we have seen that if features are completely off and they don't correlate with the rest, then in that case, there is a wide range of sub-values within our input vector. So to summarize, I have presented you two different families of method. One, we call it as DDCC. In particular, we recently introduced locality, and we are trying to sample better the amplitude space so we can actually increase the applicability of these models. And currently, we're also working on the convergence of the project equations and on the parenthesis T through this scheme. In the second case, we're exploring also strongly correlated methods like the DDV2RDM that I show you today. Before I finish, I would like to make an announcement. We have secured funding from our college for 5 new faculty positions in our university on science-informed AI. And this is an effort that started from the Department of Mathematics. So we will have 5 hires. 2 will be on the Department of Mathematics, 1 for physics, 1 for chemistry, and 1 for manufacturing, for the engineering. So this year we have 2 positions at the geometric deep learning and physics informed machine learning. But next year we'll have a position at the junior level, at the the assistant professor level for chemistry informed AI. So if you are interested, let me know. I can provide to you with more information about these opportunities. So with that, I would like to thank, first of all, the funding agencies, in particular NSF. This project has been supported by NSF. I need to thank Jacob, who started all these projects a few years ago. Justin, who was an undergraduate in our group. Now he's working as a PhD student at the Florida State University. Greer, and Varuna, who are pushing these projects nowadays. Greer just graduated, and he's continuing at the University of Toronto for a postdoc. And Varuna is about to graduate in a few months. And of course, with that, I would like to thank you for your kind attention.
Thank you. Questions?
Thanks. Very exciting results. So, quick question. So, the largest basis set I saw was augmented double zeta. Like, how does it work in triple or quadruple?
Well, we have tried to augment the triple zeta. It's the same behavior as long as we have the data. So, of course, by adding more larger basis sets, the effect is more amplitudes. So, as long as we can sample properly the additional amplitudes that we introduce, then we have the same effect.
More questions?
Yeah. When you showed the water clusters, you were showing the energy error. Was that a total energy or an interaction energy?
Sorry, for what model?
When you were showing the water clusters.
Yes.
Was that a total energy or interaction energy?
That's the total correlation energy of the full hexamer, yes.
Do you have any commentary on, or do you remember the figures for how it performed specifically on the non-covalent interactions for those systems?
Yes. This is work in progress. So far, interaction energies are more off than we were expecting. That's why this is our next target. It's something that we would like to solve, but first we need to solve the issue with the proper sampling. Yeah.
Thank you.
Very good question.
Any more questions? If not, let's thank the speaker once more.